Hello, everybody. Thank you for coming to my talk about Dvb-T hacking. A bit before we start, a little bit about myself. So my name is Amihai Neiderman. I'm a security researcher from Israel. I work as the head of research at Equas Technologies, and I mostly do vulnerabilities at home for fun, and mostly that's what I do at work. Now, what exactly is Dvb-T? Dvb-T stands for Digital Video Broadcasting Terrestrial, and it's just a standard for digital video broadcasting. So if you remember these old antennas that we used to have on rooftops, then it's gone. And if you remember this as well, and then it's gone. What we have today is receivers like this that you see here. And the way it works is you go to the store, you buy a receiver, something similar to this, plug into your TV with an antenna, and you have digital video broadcasting. Now, the name of the network in Israel is Idan Plus, so I might use it several times during the presentation, so just for you to follow. The receivers are fairly cheap. They cost around $50 US. And one of the most popular one is the Silverline HD2613N, which is made by a Chinese company called M-Star and sold by a company called Benda Magnetics in Israel. Now, why researching Dvb-T receivers in the first place? Now, it's really fun researching IoT devices. I really love it. That's my hobby. And at some point, I realized that probably all the routers in the world are being written by the exact same person, because you can find the exact same vulnerabilities every time. And it's kind of boring now. I have a smart TV, but I don't want to break it. It's pretty expensive. I don't have and don't know a single person with a smart refrigerator, though I really want to research one. And the receivers are pretty cheap, and that's what I was going for. So I just went to the store, asked for the cheapest one that they had. They gave me this one, and I took it home with me. Now, for those of you who haven't been to any of my previous talks, and that makes sense because I usually give them in Israel, I usually start working with a simple plan with 3 steps, like 1, 2, 3, profit, and expand it as I go. I won't be doing this today, though. Instead, I'm going to give you the outline of my plan. And I had a single goal in mind. I really want to hack it. And if possible, to hack it over the air, because RF is fun. Everybody are hacking stuff over TCP/IP. I want to do something, I want to do RF-related stuff. Now, in order to hack it, I first had to get the firmware, get the correct firmware, the one I have on my box, reverse the firmware for a while, spend a few hours working on this, open the casing, get it executed, happens, get shell access, reverse some more, find a bug, exploit that bug in Yay. And Yay, in this case, is giving a talk here in Japan. It's pretty cool. So I started with getting the firmware itself. And there are basically, essentially, 2 ways to get the firmware for a device you're trying to research. The first one is to go to download the firmware update, going to the manufacturer's site or to some bizarre Chinese website that have everything in them, or to extract it from the device itself. I tried going to the manufacturer's site, but they only had outdated versions of the firmware and some localized one. And I was pretty certain that it's not the ones that I have on my box. And tried going to bizarre Chinese websites, but I didn't find anything interesting. But what I did find was this. Those are leaked CPU schematics for an M-Star CPU. It's a MIPS CPU, remember this. And it's the same CPU that they're using in the receiver that I bought. And if we take a closer look, then you can see here there are 2 lines labeled UART-RX and UART-TX. And this is just a serial connection. So maybe, just maybe, there is a console we can connect to. And we can use this console to dump important files for later on for research. So I want to get shell access, like I said, to dump the firmware. So I'll open the case, and you can see right away that the circuit board doesn't take much of the space inside the box. They could make it like 3 times smaller and much cheaper. So all of this space is just wasted space. And if we take a closer look, then the first thing we want to do is when we're researching something like that is to start identifying the parts. So we can see the circuit board from a closer look, and that's the first part. Don't touch this, you get electrocuted. We can find the CPU. It's pretty easy to spot because of the large heatsink. We can see the serial connection here. We can enlarge it a little bit. And there are some other smaller parts that are pretty hard to see, but we really need to find a way to get a better look at them. So I bought this really cheap microscope at Deal Extreme to take close-up pictures. And it really helped me to identify some of the parts. So for example, that's the flash chip. It's kind of hard to see, but there are some writings on it. So I was able to identify the exact brand and version of the chip. And after doing so, I could build like a basic block scheme of the device. So we have the CPU connected to a USB device. We have 64 megabit serial flash and 2 DDR RAM memory. Now, I really want to get shell access, so I took the circuit board out. That's just me soldering some wires to the serial connection. Like I said before, if we could get serial connection and maybe there's a console, we can maybe dump the flash out of the device, the firmware itself. Now, I was able to identify from the 3 pins which is the TX, RX, and ground. And the way I did it was a pretty cool trick that I just learned from a weblog I was reading. Some guy suggested plugging in a voltmeter to each of the pins while the device is booting up to see which one of them toggles between -5 and 5 volts. That's probably the TX trying to write stuff to the serial while booting up. Now, after doing so, I still need a way to read the data that's trying to write. So I bought this fake FTDI from eBay. What it does, it just basically translates serial data to USB and vice versa. It's really cool. If you want to get into hardware hacking, that's a must. And I had this setup after doing that. So you can see my computer connected to the box itself. It's in my living room. And, well, my wife isn't here, so I can say I'm not really sorry for the mess. And I boot up the device, and you can see that it spills a lot of data over the serial connection. So it says, hello, U-boot. This means it's using a U-boot bootloader. It's a pretty common bootloader for embedded IoT devices. I tried some stuff about the board itself. And I waited for the shell to come up. And I waited for a couple of minutes. And 2 minutes later, all I got was an endless loop of this string. Says, no this country in EAT, which means basically nothing to me. And it wasn't quite what I was expecting for. I really wanted something like here on the right that you can see. I want a real shell, and I didn't get it. So I tried a different approach. I decided to extract it directly from the flash memory itself. And like I said, I was able to identify the exact brand and version of the flash. So I downloaded the datasheet for it from the manufacturer's site. And this actually helped me to get the functional block diagram, and I knew what every leg on the chip actually does. And I also learned that it uses SPI protocol for its communication protocol. So I just took the circuit board, took it upside down, and I didn't really want to take the flash chip out because it was kind of hard to solder it out and then solder it back in. So I did something that I know it could make electrical engineers mortified by that. But I just soldered some wires to the back of the legs in the back of the circuit board where the flash chip is coming out a little bit. And when I had this set up, I just took my Arduino, plugged all the pins to the right place, and somebody already implemented an Arduino SPI library and implemented the protocol for this specific chip. So I didn't have to do a lot, just told it to dump everything to my computer. Now, it took some time, but eventually I got to the point that I could start reversing the firmware, and that's actually what I wanted. Now, I reversed it for a while, and those are some of my notes. And the first thing that I learned that it runs ECOS. ECOS is just an embedded operation system, a pretty lightweight one. It doesn't have any shell support. They didn't compile it in. There are also no debugging options, not even EJTAG, which is pretty common for various MIPS CPUs. And there is a lot of code. And reversing it statically is going to take a lot of time, and it's going to be kind of hard. And it was meant to be like a fun project at home, so I didn't want to work really hard. I really need a debugger, something that I'm used to. Otherwise, it's going to be really hard. And I thought, well, what will MacGyver do? He's going to build a debugger. So I decided to build one. And I made a list of what a debugger should be able to do, some requirements. Starting with inserting breakpoints, which is pretty important, reading and writing from memory, modifying the program code, reading and setting CPU registers, single-stepping, and the debugger must be able to talk to debuggy, which is an actual problem here because the debuggy is a box sitting on my table and not a program like I'm used to. So I need to find a way for them to talk. And with that in mind, I thought that debugger could be made of two parts. It could be made out of a lightweight server that runs on the box itself, and a client running on my laptop implementing all the state machine and all the complicated handling. But there's still a question of how they're going to talk to each other. So if you remember, I have this really neat setup in my living room. So I have the box sitting here connected to my computer using the serial connection. And I know I can read data from it. The question is if I can actually write data to it, because there is what I think is an Rx port on the box. I think that I identified it correctly. But I need to prove that before I could start writing the debugger itself. So I started reversing the easiest part I could find, the bootloader. It's an M-star bootloader. It's called mboot. It has a lot of easy-to-understand code. It writes a lot of data to the serial port. And maybe it's also reads something out of it. So I started reversing. And on one of the first stages of the boot process, I found this piece of code. And you can see here that it says, hit any key to stop auto boot. Now, it's interesting because of two things. First of all, it writes this string to the serial connection. So I found a function that I called it myPrint. You can see it here in the assembly instructions. I call it myPrint. So that's a function that actually writes to the serial. And now it waits for user input over the serial. So I reverse some more. And I found this function, and you can see that what it does, it waits until the lower bit of this address, the BF201328 hex, is on. And when it's on, it proceeds to read from a different address, full CPU word, to one of the registers and return it. So now I know how to read and write from the serial connection. The serial is just mapped to a RAM address. And that's actually what I needed. And now it's time to start writing the debugger itself. Now, before writing the debugger, I thought, how can I implement breakpoints? Because like I said before, it's one of the most important debugging features that you have. And this could be done in different ways depending on the architecture that you're running on. For example, if you're running on x86, you could use hardware breakpoints using specific registers meant for this. You could use JTAG if you have support for this on your CPU. You could use special instructions like break instruction. And you can do jump patching, which is pretty lame, actually. And the way it works, for example, if you want to put a breakpoint on this line here, then what we do, we just replace the original instruction with a break instruction. We save the original data somewhere else that we can restore it for later. And whenever the program counter hits this breakpoint, then usually on MIPS you will get an exception. And the exception, what will happen is that the program execution will be moved to this snippet of code. It's called the exception vector handler. And it's almost always located on this address 80,180 in MIPS. And what it essentially does, whenever you get an exception, then the CPU can get the exception number, And it goes to a special, what's called the exception vector, goes to a special array with specific handlers to each of the exceptions. So the break instruction in MIPS causes an exception number 9. And we can just replace the breakpoint handler, the handler for exception number 9, with our debugger code. So if we put it to our server client design, whenever the program counter hits the breakpoint, then we jump to our server code. The server code notifies the client that sits on my PC over the serial connection that an exception happened, and the client takes it from there and decides to do whatever he wants with it. Now, I started thinking what the debugger should be, what the server should implement, because I want to make it as lightweight as possible. And to make it as lightweight as possible, I decided that it only needs to implement 4 primitives: reading a byte, writing a byte, getting a register, and setting a register. Now, if you remember the list that I made before, the list of the requirements, I can show you how I can implement each and every of those requirements using those 4 primitives. So if we take a breakpoint, for example, all a breakpoint does is just reading from memory, writing to memory. And let's say we want to put a breakpoint. All we have to do is to read the original 4 bytes of the instruction that was there, send it over the serial to the client, and save it, and write the 4 bytes that means the break instruction to that same address, and continue execution. And this is how the pseudocode will look like. And if we have a breakpoint, an exception, this is how we handle this. We check if the address that the exception happened on is the same address that we put the breakpoint on. And if it is, we just restore the original instruction and continue execution. Now, I wrote the server pretty quickly, mostly in C, some assembly, only the essential parts, the ones handling the stack. And the client was written mostly in Python. But I still need to find a way to upload the server into the memory of the box. Because if it's having on my computer, doesn't really help me a lot. I need to put it on the box itself. Now, if you remember that piece of code that says hit any key from before, then if you actually press any key during the boot process over the serial connection, then you get a pretty sophisticated menu. It's an MSR U-boot mixed menu. And you can use some of the commands that they have there to upload a custom binary into the memory of the device. I think it's used mostly for firmware updates or for diagnostics. And what I did, I just made a patch firmware binary with a patched exception vector. Like I said before, I just patched the pointer to my server code and added the server code snippet to the end of the binary and loaded into the memory of the device. Now, you know what? When you debug a program, you could press Control-C and stop the execution when you're like debugging something with GDB on your computer. I want to have the same ability when researching this. So I didn't have a keyboard, but what I did have was a remote control. So I found a function that handles volume up. So whenever you press volume up in the remote control, this function gets called. I patched this function with a break instruction. So now whenever you press volume up in the remote control, you get this on my computer. This is an actual debugger running on my laptop. And you can see all the registers in the device itself. And you can start using the debugger. It's a mix of GDB and WinDebug commands, the ones I like from each of the debuggers. And it's an actual fully functioning debugger now. And now I can actually start working. And if you remember my goal list, and then, so if you remember my goal list, then I added building a debugger because I built an embedded debugger. It was the first time for me. Now I still need to find a bug. So it's time to find a bug. So what exactly is Dvb-T? And that's the manual that explains what Dvb-T is. And Dvb-T is hundreds of highly technical implementation-related data. It's 4 pages of abbreviations. It's a lot of graphs that I have no understanding of them. everything is called tables there, and they are actually pretty fairly documented. And I call them packets because it's easier for me to understand that in packets form and not in table form. And someone had to make a mistake while implementing this thing because the protocol is huge. There's so much to it. The question is where? Where did somebody make that mistake? So this is a protocol by me. And I tried reading the ETSI manual. It's the European Telecommunications Standard Institute. And I didn't understand a thing from there. It's written in a language that I don't know who it's meant to be, who's supposed to read it, but I think I'm pretty technical, but I didn't understand most of it. And after trying to read it, I wasn't really sure where to start. And there are a few courses of action here. None is better than the other. You can learn really good about Dvb-T protocol, I thought of doing this, and then find the soft spot, the place that looks the most buggy area. I thought of starting with the easy to parse packets and move on, like find a really, really simple one, packet or table, whatever you want to call it, and maybe it will help me to understand what's going on in the device. I thought of going to the more complicated packets, because maybe somebody had to mess up there, because it's really hard to implement that, but it will take more time for me to understand, or I could use fuzzing. So I thought of starting with fuzzing. Sounded fun. So what I did, I placed a low-level hook using my debugger. So it was the first time using it. Or actually I used it a lot to find that function. So I placed a low-level hook on a packet. I called it packet receive, which is the lowest level function that could find that actually communicates with the radio device in the box. That's what actually reads the packet from the air. You can say that. And I thought of using a generic debugger, generic fuzzer to generate some, to fuzz around about 20 tables or packets. All you have to do is to make sure that the CRC is okay. So this is how a packet looks like. You can see there is a CRC in the end, and there is a lot of data to fuzz around. There are a lot of parts, so if you think of it as a struct, there's a lot of variables to fuzz around. And we can actually run this command. This is just how you call this specific fuzzer. You can run this command, and all it does is takes a legitimate packet and change it 1% of the time. So you can generate thousands of those packets and use the debugger to place them directly into the memory of the device and check how the device behaves. If it crashes, then you get a crash log. Well, you actually jump to the debugger, you can see how it crashed. And this held for like 20 seconds. When I first tried to do the fuzzing, I tried to reverse the simplest the simplest packet I could find to just fuzz her around. And I found this. It's called the time offset table packet. And I have no idea what it does. I think it does something with time. And you can see here that you can place a lot of descriptors inside this packet. And there is a variable called n. So you can place n descriptors inside. And n is defined as the value of descriptor loop length. It can be 12-bit at most. So you can put about 4,000 of those descriptors inside. And each of the descriptors looks something like this. And you can see that, first of all, the descriptor doesn't have CRC. That's pretty cool, because now you can put memory as you like, and you don't have to be constrained by the CRC. And you can see the descriptor has an n variable of itself. And n is defined as the descriptor length. It could be 8-bit at most, but 8 bits quite a lot. And you can have about 4,000 of those. Now, when it came time to implement it, they decided that n always equal to 1. So the size of the descriptor inside the TOT packet is always 15 bytes. And that's not true. It could be bigger. But that's what they decided, because who needs more data, right? And this is, let's say that's the code that they wrote. It's a pseudocode of the assembly code that I saw. And we can see here that they always reading one. They decide they're going to read only one descriptor from the TOT packet, which is fine. But they assume that the descriptor is always 15 bytes in size, and the person that wrote the function that I call it my parse time offset descriptor actually doesn't assume that. He assumes that the descriptor could have varying length. So they trying to read something in size that I can control into a 15 bytes struct on the stack. And what we essentially get here is a stack overflow, a pretty simple one, actually. That's a real problem using someone else's code, I think. So like I said, that's a pretty simple stack overflow. Whenever they return, we can just pawn it. And back to my goal list, I found a bug. Now it's time to exploit it. Now, it's a stack overflow. It's pretty easy to exploit, really easy, because it's an embedded device. We don't have ASLR. We don't have annex bit. The cache, for some reason, is set on write-through in the device. That means there's no actual cache, and caching is the only actual problem that you have when trying to exploit MIPS devices, MIPS CPU devices. And so it was pretty easy to exploit. And when you see this piece of code when trying to exploit MIPS, you know that everything's going to be all right. So if you look at the first line of code here, you're seeing that it actually loads the return address from the stack. And that's something not very common for MIPS devices. So when you have something like this, then all the stars align, and you know it's going to be really, really easy to exploit. All you had to do is, like in every Stack Overflow tutorial, you do a jump to the stack pointer, and you can actually execute code like this. Now, this thing is pretty dumb. It doesn't do a lot. It can transmit. It can do anything. But we managed to pawn this over the air. You can use a USRP or an HackRF to do it. Everything is already implemented to send the packets over the air. But after doing that, you can't really do anything with it. You don't know if you execute code on it. But this thing is actually connected to smart TV, like the one that I have at home. So maybe you could take it from there after you after you execute code on this. You can maybe hack your TV. Thank you very much.